Hi, I'm Neil, and welcome to my walkthrough of implementing GPT-2 from scratch. This is the second part in my What is a Transformer walkthrough series. The first part explains what a transformer is conceptually, and what the different parts of it, like attention, are and do. This part is just me actually coding the model. If you already feel like you basically know what a transformer is, you don't need to watch part 1. If you feel confused and stuck, you should probably go back and watch it. In this video, I'm just going to write GPT-2 from scratch and talk through what I'm doing. In the description, I link to a template notebook where you can follow along at home and try to write the model yourself. I think that the truest sign that you understand something is that you can just write the code for the model yourself from scratch without referencing a solution and without copying and pasting. My hope is that by the end of this video, you're going to be capable of that yourself. The notebook comes with tests, so you can make sure that each bit you're doing is correct. And yeah, I hope you enjoy the ride. A brief note on why I've made this tutorial, when there already exist a bunch of other transformer tutorials. As I discussed a bit in part 1, I'm a mechanistic interpretability of language models researcher. My job is to take a language model that is capable of doing some task, like, I don't know, how GPT-3 can write poetry, and then say, okay, the model has learned some algorithm to do this, but it has no incentive to make this algorithm, like, nice and legible to humans, so we have no idea how it works. But if we put in enough effort and find the right techniques, it turns out that in practice we often can actually reverse engineer how it works. Mechanistic interpretability of language models is this exciting young field about trying to do this and push it as much as we can. We have no idea how you write computer programs that can do things like generate poetry, yet we have weights for a model, essentially a computer program, that can do this. This deeply offends me, and I would like to solve it. In order to do interpretability, you need to really understand how a model works. What are the moving parts, and what is the internal computation that is happening? I find achieving this really satisfying. If you enjoy this video, and feeling like you really get what a transformer is, I highly encourage you to go check out mechanistic interpretability, and see if you want to dig more into the field. In the description, I link to a sequence I've written called 200 Concrete Open Problems in Mechanistic Interpretability, where I give ideas on how to scale up, papers to read, tooling. Notably, I wrote a library called Transformer Lens. The code we write in this video is actually the basic transformer implementation that Transformer Lens is built on, which lets you load in open source models like GPT-2 and probe around at what's going on inside of them. The eponymous list of 200 concrete open problems, a map of which areas of the field I think are promising and rich to explore, and ways someone new to the field could get started on. Without further ado, let's jump into coding up what is a transformer. I recommend pausing the video after I've explained something and trying to write the code yourself in the template notebook without referencing and definitely without copying and pasting. I also think just watching through the video and then taking the template notebook and seeing how far you can get from memory or from your notes is a pretty solid exercise. If you're interested in hard mode, not watching the video, taking the template, trying to fill it out, and seeing how far you get. Each transformer component comes with a test, which checks that if you load in the GPT-2 weights into your implementation, it gives the correct output. Hopefully this can give you enough feedback that you can keep on the right track. And yeah, let's jump into coding GPT-2 from scratch. Hello! If you've just come here, then I'm going to briefly recap how a transformer works. High-level architecture, you have these input tokens. You learn a lookup table, mapping them to residual stream vectors. You have a series of transformer blocks, which have attention layers moving info between positions, MLP layers processing information at a position. Everything happens at parallel at each position. Each layer reads and writes the residual stream. Positional information is added to the residual stream via a lookup table as a learned thing. At the start of each read operation, to attention MLP into the unembed, there is a LayerNorm which centers and normalizes the vector to be mean 0 and variance 1, and then applies an arbitrary scaling and translation because YOLO, and then we unembed the residual stream at the very end, where we map it to a vector of logits just via a linear map with a final layer norm there. Cool, let's go write some code. So, actually writing code. Woo, the promise of this tutorial. And let's just write out some high-level sections. So first we're going to do LayerNorm, because LayerNorm's kind of easy. Then we're going to do positional embedding. Then we're going to do attention. Then we're going to do MLP. Then we're going to do Unembedding. So here we should do a transformer block. And here we should do a full transformer, and then we're done. And can maybe do some tests. But yeah, alright, so LayerNorm. Conceptually, it's gonna make mean 0, scale to have norm 1, scale to have variance 1, scale with learned weights. Note that this scaling divides the entire vector by a constant. This element-wise multiplies the vector with learned constants. Scalar, not constant, because this is a function of the vector. Translate with learned bias. Let's go write some code. Class LayerNorm. This is just PyTorch boilerplate. Oh yeah, I'm going to make a config object to pass around everywhere. And we'll just kind of edit it as I go. Config, and I think if I do this, then the model is a working data class. Yeah, I'm just gonna write in defaults for what everything should be. And yeah, so I'll update this as I go. So the first thing we want to put in is the size of the residual stream. We're going to need to know that in order to make the weights of our residual layer. But yeah, so what we do is we've got this vector of learned weights that I'm going to call W. Yeah, PyTorch syntax, generator, constant vector of all ones. This means make it a parameter, which says train this when I do gradient steps, and move this with me when I move the model to different devices, and just some various nice helper functions. And I need to import the neural network bit of torch. So I can put nn everywhere rather than torch.nn, because I don't have time for that. And then we define a bias, which is the same, but we initialize it as zeros. The intuition here is just by default, we don't want to change the norm. Variance 1, this is reasonable. By default, we don't want to change the mean. Mean 0, this is reasonable. Now, we have the forward, so this takes in a residual vector. Then we subtract off the mean. So for this, I'm going to use inops.reduce. So the way that inops.reduce works, so first, really important, always write down your shape. I'm just going to print, let's say if config.debug print shape. I'm just going to add a flag here so that when I'm debugging, it will just always print out the shapes of things, because that's just really helpful. And so the shape is going to be batch by position by dmodel. And I'm going to want to take the mean along the dmodel dimension. So the syntax for that in inops is you write the names of the axes at the start, you write the names of the axes at the end, you write the tensor, and then you write the reduction you want to do, and this just works. Now we figure out the scaling factor. I'm going to do this as a separate thing because it's a bit more involved. So conceptually, we want to calculate the variance and square root it. We also add in an epsilon, just a tiny number, so we don't divide by 0. I love Copilot. So the variance is going to be the sum of squares divided by n, so mean. Yeah, basically the same thing we did earlier. And then we add in the config.LayerNorm epsilon, which I know people often default to be 1e minus 5. I don't think it really matters. You know, sometimes you'll get 0 vectors, and you'd rather not be dividing by 0, because that sucks. And then we want to square it. The .pow2 is the most convenient notation for that in PyTorch. You could also do **2. And then we want to square root this, and that we do with just the .square root. And yeah, that just works. And now we have a residual dash scale. And now we have the normalized thing, which is just that. Yeah, let's call this normalized. And now we scale and translate the normalized, and then we return it. Let's just print the shape of the output. This is one of the many activations that we get access to the shapes of inside Easy Transformer. Actually, I'm just going to go and print out all activations of the reference model. It's just really useful to have a clear picture in your head of what the shapes are. Shapes are basically just like variable types for tensors. And so here, what I'm going to do is for activation name, comma, activation in the cache object I took earlier. This is an activation cache object, which is a wrapper around a dictionary with a lot of helper methods. Here we just want the dictionary. And now I'm going to print the activation name followed by the activation shape. I'm just going to add some random code here saying only print things if it's in the first block, because each block is symmetric, so if you print the same thing for every block, it's a massive pain. And yeah, so key batch equals 1, position equals 35, dmodel equals 768, number of heads equals 12, number of layers equals 12, size of the MLP is 4 times 768, which is going to be 30,072, I think, but I'm just going to go actually calculate that. Oh, that's right, cute. And then the internal dimension of a head is... And the internal dimension of a head is 768 divided by 12, which is 64. And yeah, so like looking through this, we can be like, for the purposes of the LayerNorm, we've got the scale. So the scale has size batch by position by a dummy dimension. I should actually go add in the dummy dimension. That's pretty useful. The key thing here being you want to make sure you've got a dummy dimension remaining, so that when you divide, let's just put a 1 in here. You want to make sure you've got a dummy dimension so that when you divide by things, it like broadcasts to the right shape rather than thinking, oh, I should divide the demodel dimension by the position axis, and it's terrible. And so the scale is batch by position by dummy, the output is batch by position by demodel, yay. Now, I think I'm going to go write some tests to make sure that I'm writing sensible things. Generally, just having like really lightweight tests as you go is a pretty good way to do development. The kind of naive test, generate random inputs of the right shape, input to your model, check for errors. Let's call this rand float test that can take in a class name, take in a config object, take in a shape. And then it initializes the class. Yeah, initializes the class. Then it... I don't even need to pass it a config object. Then we make an example layer, then we generate a random input. Rand_n just means like standard Gaussians. And then we print output shape. And then we return the output. Alright, now let's go test our test. What did I call the test? Rand float test. That was a sensible name. And the shape is, I don't know, 2 by 4 by 768. Can it do things? It can't, because I never defined config. That is a reasonable thing to complain about. Let's make a few more tests while that's running. Let's make a rand_int test, which generates random integers, say between 100 and 1000, which we can use to test things that take tokens as inputs. And let's make a load GPT-2 test that takes in a class, and takes in the GPT-2 model, and takes in a shape, and generates, takes the relevant layer from GPT-2, takes in the shape, and generates random inputs. Or, I'm just going to go write this and then I'm going to explain what I did. Copilot. I love Copilot. Following the exact details here are not super important. That is surprisingly close. So we're going to use the GPT-2 cache, which maybe we need to pass in, but maybe not. We're going to get a reference input. Then we're going to pass this into the layer and get the output. Then we're going to print the reference output shape. And now we're going to compare them using the torch is close function. Torch is close is normally kind of irritating, because it has really harsh tolerances. So I'm going to put like, if things have ratios differing by 1e minus 3, or absolute difference of like 1e minus 4, I'm happy. And then print the... Again, you really don't need to follow exactly what I'm doing. I'm just writing code that will print a percentage of how many things were correct. And then I can just return the output. And great, this is hopefully a functional test. Why is this unhappy? Okay, I'm going to pause this and go deep. Alright, so slightly embarrassing. That was the dumb bug where INOPS wanted to put the tensor first rather than second. It's now fixed, so all is good in the world. I'm also gonna add a cute line to each of these tests saying print get corner of the output. Get corner is one of the utility functions in Easy Transformer that just prints the first k elements, default k defaults to 3, along every axis of the transformer, and it's just very useful. Yeah, it's just a very useful thing for visually looking at a tensor without polluting your notebook with just enormous printouts that are too big to read. So now I'm going to do my rand float test, and everything works. And I'm going to rerun the cell. Yeah, that looks pretty sane. Final problem. Alright. Fixed 2 more random bugs around things not being on CUDA and random shit like that. But the important thing is, this now works. Just to briefly explain what this test is doing, What this does is it takes in an instance of that layer from my reference model, it takes in the name of the activation that went into it. In this case, resid post means the residual stream at the end of the layer. It's like this part of the block, and 11 is the final layer because there are 12 layers. It just verifies that they're the same thing, and they've all got sensible sizes, and 100% of the values are correct, so life is good. So now I'm going to code the embedding, basically a lookup table from tokens to residual stream vectors. I'm just going to go and briefly add 2 adjustments to this. Strict equals false means no, scratch that. Random details, not important. Let's make this support putting in things in the cache and things not in the cache. So what I'm doing here is I'm just adding a statement saying, if this is a string, look it up in the dictionary. Otherwise, assume it's a tensor. Because I can't be bothered to write deeply principled code here. You really do not need to follow all of the random shit that is me writing various tests, except for the meta-level thing of writing tests good. So now I'm going to write the embedding. If we just go back up here, so we printed out all the activations, and here we saw that the activation from the embedding was batch by sequence by demodel. We can also print all of the parameter shapes. So I'm first going to just print out the model. This just shows me the structure. Embed, pos embed. All of these hooks are just easy transformer boilerplate for getting access to activations. For the purposes of this tutorial, it doesn't really matter. The important thing is just these will access the activations of the same names in what I add to my models. And then for name param in reference GPT-2 not named parameters. Yeah, so this just creates an iterable giving the tuple of name of weight matrix. I'm going to add in the same boilerplate code as before to not print a bunch of parallel stuff, and I'm also going to close this because it's too big. Yeah, so here we see that the embedding contains a single weight matrix WE, which is devocab by demodel. And my code did not work. Oh, it's because I call it name rather than activation name. Whatever. Great. WE, devocab, demodel. Again, when I randomly go on tangents or mutter to myself, you don't need to care. Let's print the reference models config for reference, but note there's lots of shit in here we don't need to care about. Note there's a lot of stuff we don't care about in here to do with library internals or other architectures. It's kind of a mess, but devocab 5027. So yeah, now we can go write the embedding. This is PyTorch boilerplate for I'm defining a module. We define the embedding matrix as, yeah, Copilot just knows what it's doing, apparently. Here we're going to fill it in with a normal of standard deviation 0.02. Let's add this to the config. Why is it 0.02? I don't know, man. That's what GPT-2 did. Most people just cargo cult GPT-2 because no one knows what they're doing. Hilariously, GPT-2 uses the same initialization range of 0.02 for everything, including all of the models of different scales, and GPT-Neo uses it for even larger models. And my best hypothesis isn't, it just doesn't matter because LayerNorm scales everything. But it's kind of unprintable and makes me sad. If you're interested in going deep into hyperparameters, there's this paper on new parameterization that has a lot of interesting theory there that came out earlier this year, but that is so out of scope for what we're doing today. So yeah, the embedding takes in inputs. I don't actually think this is correct, but it's a valiant effort by Copilot. Here I'm going to do a bit of fancy indexing. You really do not need to understand what I'm doing. Essentially, this code will give me something whose shape is batch by position by demodel. So what this is doing is I'm indexing with a batch by position tensor on the devocab axis of the embedding matrix, and that expands it to a batch by position thing and gets rid of the devocab using the integers in here as indexes. You really don't need to understand that though. And yeah, I want to do a rand int test and load GPT-2 test. Int because tokens. And load GPT-2 test. And let's just actually feed it the input tokens. Cool. Why is that sad? Actually, it occurred to me I can just go look at my reference code. So let's go open the relevant file, which in this case is components.py, and look at how I define the embedding. Or no, wrong file. I initialize things in a separate file for fairly unimportant reasons. Cool. Here I use nn.init.normal after defining an empty thing. So let's just do that. So empty just means create an empty tensor and of the given shape. And this means random boring boilerplate. Great. And this is working. Recap, got an embedding. Got a matrix of vocab by demodel. The demodel dimension is the look to upper vector. The devocab dimension is the lookup table dimension, where you index in with a given token, and it's a lookup table. It's magic. And this is random tensor bullshit for looking up stuff. Now we're going to do a positional embedding. So the way positional embeddings work is they're, again, a lookup table. But this time, the way the lookup table works is that I'm just going to copy and paste this boilerplate because I'm going to use it in every module. Yeah, so the way the positional embedding works is, you've got a max context by demodel tensor. N context just means what's the biggest thing that could fit into your context. For GPT-2 it's 1024 because everyone loves powers of 2, doesn't matter a ton. For GPT-3 it's 2048, and I think the latest models on the API are 4096. Yeah, so this is again a lookup table, but this time it's a lookup table for the index of the token. So just the index of the position in the range. Note that we only go up to the max position length that we're willing to accept into the model, and we can't accept things of arbitrary inputs. There are other positional schemes that can, but who cares? And now we can just define self, forward, tokens. The thing we want is going to be not quite. So the thing we want is a thing whose shape is batch by position by demodel. But it's also going to be exactly the same across the batch. So what we do is we take the position dimension of the token. Dot size 1 means what is the size of the 1th dimension, which is position. Then we broadcast up. So we just repeat along the dimension. That is completely correct. Thanks, Copilot. Yeah, we just broadcast up along the batch with this, and we're happy. Now I want to do 2 tests. Thank you, Copilot. Alright, why is it unhappy? Oh, it's because I indexed in with the number that is the position rather than telling it go until that point. Great. This is happy, and the shape that I got out is, yep, it's the same as the reference shape, so this is definitely just working. So now we've got attention. And attention is a lot more involved, so I'm gonna try to go more slowly here. The way attention works is step 1, produce an attention pattern for each destination token probability distribution over previous tokens, including current token. Step 2, move information from source tokens to destination token using attention pattern, move equals apply linear map. But the way it's actually implemented is you break this down into a linear map from input to query and key vectors, where the destination token has a query, the source token has a key. Intuitively, the query is what am I looking for? And the key is what do I have to offer? These will have shape, batch by position, by head index, by dhead, because each head will have its own query and key, and they all have dimensionality, the internal dimension of the tensor. Then we dot product every pair of queries and keys to get a batch by head index, by query position, by key position tensor. Query pos and key pos are both length position, which is why I'm separating them. The first axis is the destination, the second axis is the source. These are attention scores. Then we scale and mask attention scores to make it lower triangular, i.e. causal. Then we softmax row-wise to get a probability distribution along the key pos dimension. The masking is to make it causal, so things can only go backwards. And then, that's a pattern. Then step 2, kind of happening in parallel, we linear map from input to value. This has the same shape as key and query. This is internal to each head. The head index mentioned just because it's really useful to have everything be tensorized. You can totally think about a for loop just going over each head if that feels more intuitive to you. And importantly, this is key position. Then we mix along the key position with the attention pattern to get Z, a mixed value, which has exactly the same shape, but is now over the query positions. Then we apply a map to output, which is batch by position by demodel. Here, position equals query pos, and we've summed over all heads. And that is attention. And skimming back up to look at the weight matrices. On the weight matrices, we've got map to query, map to key, map to value, map to output. General convention, all of my matrices will write multiply. This is the input dimension, this is the output dimension, and this is the head index dimension because we're multiplying in parallel. It's head index, demodel, dhead, because these map residual stream to internal dimension. Head index, dhead, demodel, because this maps from internal dimension for each head to output dimension. These are the biases. They just have the shape of the output of each matrix and will get broadcast across every position, every batch. Here are the attention activations. We see that queries, keys, values, and Z, or mixed values, have shape batch, position, head index, dhead. Attention scores and attention have shape batch, head index, query position, key position. Though from this you can't tell the difference between query and key, obviously. Note that head index is now swapped order with position, and the output is batch by position by demodel because, it's an output. It adds the residual stream. Everything in the residual stream has exactly the same shape. A thing which is kind of worth doing with attention is just actually visualizing attention patterns and just getting a sense for what they actually are. And for this, I'm going to use a library Anthropic open source called PySvelt. I'm just going to write some boilerplate code. You don't need to care about what the code is. Yeah, let's look at the layer 0 heads. Syntax for looking up activations. You've got blocks, you've got index of layer, you've got name of layer within a block, you've got name of activation. And I call the attention patterns attention or atten for not very important reasons. Yeah, why is this annoying? Oh, it wants things to be in the opposite order, so I need to permute things. Oh, I need to get rid of the batch dimension. What's going on here is, so if I click on a head, this is a query by key map of the attention. So for each row, say this query, so if we hover over a token, we can see the attention pattern. This is the 5th token, so there are 5 previous key positions or source positions moving to this destination token. And this mostly moves information from the 1st token, presumably because this head is just kind of off most of the time, but attention needs to add to 1, so it just rests everything on this token. This is why, by default, I add an end-of-text token, even though GPT-2 was not trained with that. Here's a previous token head. Oh no, sorry, this is a current token head. Why does this exist? Presumably the model just wants to apply some linear map to itself here. Oh, maybe it's a duplicate token head, it attends to copies of the current token? I don't know. This is kind of funky. What's the other thing that repeats itself? Yeah, it looks like a duplicate token head. Interesting. This is another self head. This is mostly a self head, but a bit messier. Another self head. Surely there's previous token heads in here somewhere. Okay, there's normally... Yeah, this is a head that attends to recent tokens. It's not quite a previous token head, but it's basically close enough. Generally, you tend to get previous token heads in early layers because it's just a very basic thing that models can want to do. Let's look at layer 1 and see if layer 1 has anything. But yeah, in general, just interactive visualizations are awesome. Getting in the habit of just playing around with shit is just really useful and good and pretty healthy. And I think this is just the natural thing you should do whenever you start any investigation like this. Fascinating. I'm failing to find a previous token head. I did not expect that. Yeah, I recommend just playing around with this and trying to get a taste of how does an attention pattern actually behave? What is this object? Why does it matter? But great, I'm now going to go and define what the attention class is. And let's make sure I keep this in view. Good thing I copied that earlier. So now I'm going to define a lot of objects. Each of these weights is a nheads by dmodel by dhead thing. I'm just going to go add everything to config now. Let's just close the previous things. And let's say nn.init.normal. Then we're going to define the bias. So the output of WQ is going to be the nheads dimension it's going to be batch by position by nheads by dhead. So the bias should be nheads by dhead. And I'm just going to initialize this as 0, so I don't need to do the normal thing. And now I'm just going to go and do this exactly the same thing for keys and for queries, because they're just the same shape. Then I'm going to define the output, which is sufficiently similar that I'm going to initially copy and paste, but also is a different shape because it's mapping from the internal dimension to the output dimension. And so this means we swap these. Note the keyboard shortcut I'm using to do shit like this is Command D. It is my favorite keyboard shortcut. The output of this is going to be just demodel because we're also kind of collapsing and concatenating. This bias vector is 1D. And the final thing that I'm going to need to include is if I look at my reference GPT-2, I have this thing called ignore on there, which is big negative number, and it's registered as a buffer. I'll later get to why this is a thing that we care about. But for the moment, just this is the thing. And for this, I'm going to use nn.registerBuffer, which I believe is a legit function. Assuming Copilot has the syntax correct, so what I'm going to do is when I mask the model, I'm going to fill all masked things with this massive negative number, so that when we softmax, they softmax to 0, because softmax of 0 is going to give you e to the naught normalized, which is 1, normalized by a bunch of stuff, which is often much bigger than 0. And I need to make it a tensor and put it on CUDA for boring PyTorch reasons, which you don't need to care about. And so now I'm going to actually define the function. The input is normalized resid pre. This comes out from LayerNorm, so it's normalized. And it's the residual stream at the start of the layer, the block, so it's called resid pre. Then we calculate the queries. This is going to use einsum. The input residual stream has shape demodel. I think this might just be completely correct code, but I'm going to type it out anyway because it's a good exercise. But I am... oh no, wait. I want the head index to be inside. This is just kind of an arbitrary choice I made in designing this library. It's pretty reasonable to want to do things differently. I'm also going to rename this from position to query pos, and this to key pos. And now I'm going to make this about k. And here I'm going to do value. Value is also key pos because value is all about the information you move from the source position to the destination position or query position. And actually I'm going to calculate the attention pattern first and then do all the value stuff. It doesn't really matter. So now I'm going to get the attention scores. So just as a reminder, the attention scores are the dot product of every pair of queries and keys. And so this is going to be batch by query pos by n heads d head, batch key pos n heads d head to batch n heads query pos key pos. Copilot is almost but not quite correct, which is one of the reasons I don't always like to blindly trust Copilot. Note that we're dot producting every pair, including non-causal pairs, so key after query. This is a correct statement. So for random reasons, you divide by the square root of d head. The intuition is something like you're taking a dot product of a d head length vector. If you assume everything is an independent normal, then dividing by d head keeps the standard deviation the same. The mu-p paper makes a compelling case that it should just be d head rather than square root d head. GPT-Neo doesn't even have a scaling factor. It doesn't really matter. Transformers smart, they'll figure it out. Now we want to apply a mask to the attention scores. And now I'm going to go and define the mask function. So let's see. How do I want this to work? I think that might just be correct code. Thanks, Copilot. Let's fiddle with things a bit. So what we're doing here is you generate a matrix of constant matrix of all ones that's query pos by key pos. Query and key pos are normally the same, but I'm going to use different labels because sometimes they're occasionally not when you're doing generation. Puts on the right device. True means make it upper triangular, and diagonal equals 1 means offset by 1 in the positive direction. So this is taking the acausal triangle, so like things where the key position is greater than the query position, and it's making the ones and it's setting them to booleans, so they're true. And then I have not used the mask fill function before, but presumably it's saying fill this in with this ignore tensor when the mask applies. The underscore at the end of the method means this is an in-place method. So like tensor.this is going to edit the tensor rather than returning a new tensor. And yeah, we return the attention scores. Finally, we make the attention pattern, which I call atten, and this is just softmax across the final dimension, because attention scores has this shape, and we want to make it a probability distribution for each destination token, so we're softmaxing across the key pos dimension. And yeah, shape, batch, n-heads, query pos, key pos. So now we want to define z, and so z is going to be attention times v. Note that this is like a pretty weird thing to be doing. We're doing a bilinear operation where we're doing an einsum of two activations rather than an activation and learned tensor of parameters. This is just like a pretty weird thing to do. Copilot, you've done it again. This is creating the mixed value, and finally we create the output of the layer, which I'm going to call attention out, which is einsum of z and wo. So fuck it, this is just correct. And cool, this is a much more involved thing, so it would not surprise me if I fuck something up here. Copilot is so confusingly good sometimes. And let's see, so the name of this is going to be block 0, because it's the 0th block, dot hook normalized on the first layer norm. This is a hook at the end of a layer norm that gets the output of the layer norm just before it's fed into a layer. And what? Let me just Google this. Oh, it's self.registerbuffer, not nn.registerbuffer. Cool. And note that this is all happening in place, so it doesn't return anything. Funky. There is a mask variable in my implementation of attention. I don't actually know why that's necessary, so let's go check. Components file, attention class. Why do I define a mask? So I define a causal mask, which is the lower triangular thing. Oh, I think what I did is, so here I did attention the opposite way round, where I made a thing that was just true if we're on the diagonal or below, and then said, if in the apply causal mask function, I said, if mask is true, then return attention scores, otherwise return ignore. Torch.where means input booleans. If true, take the element of this thing. If false, take the element of this thing, where these are either the same shape or can be broadcast up to be the same shape. But yeah, so I'm just gonna go and edit my test to not care about the fact that some things aren't quite equal. And the way I do that is I put strict equals false in the load state dict test. Great. I have correctly coded attention. Life is good. One cute thing to observe about attention, the attention scores are the dot product of the queries and keys. But like, this is just a string of 3 einsums. Einsums are linear maps. And the composition of linear maps is just like a big linear map, and addition also factors out of the big linear map. And so this means that the attention scores are actually a bilinear form of the inputs, where we form this big matrix that is WQ at WK transpose, and multiply on one side by normalized resid pre, and multiply on the other side by normalized resid pre. But what's actually going on is that the queries and keys are a distraction, and the model has really learned a low-rank factorized matrix for each head that's demodel by demodel. And there's a similar thing with the values, because this is an einsum, this is an einsum, this is an einsum, so their composition is linear. It turns out that the WO and WV are acting on the demodel dimension, the attention is acting on the position dimension, and these are just kind of independent things. This means that you can both commute the order in which you apply the attention, like you could do attention on normalized resid, then value, then attention out, or you could do value, attention out, and then apply attention to mix things, and these are all equivalent. And also the only thing that matters is the WV matrix at the WO matrix, and everything just works. Turns out the only thing a head is doing is it's learned two low-rank factored demodel by demodel tensors. You should go watch my transformer circuits walkthrough if you want more info on that. But it's very cute. Now on to MLPs. MLPs are pretty easy, so I'm just going to go do this. It's just linear map, yellow, linear map. Oh, there's this stupid thing where there's multiple ways to implement a Jello, and GPT-2 uses one called LayerNorm, which is very, very subtly different from PyTorch Jello, and it's kind of dumb, but you need to import it. Not quite, but valiant effort. So you got the input weights, Win, and this maps demodel to DMLP, not dinner. Dang it, Copilot. And then we have nn.init.normal underscore. Yep. And now we do the same thing for output, except we swap the dimensions. And now we just do forward self.normalized resid mid. Normalized resid mid because it's the output of the LayerNorm, so it's normalized and it's in the middle of the block because we've added in the output of the attention layer. And the boilerplate is correct. Here we have pre, which means pre-activation, but pre is the name I give it in the cache, and you take in the thing, and yes, fine, this is just correct. And then you apply LayerNorm to get the post activations, and then you get MLP out. Yeah, that looks pretty correct. And now we can just apply the tests. And yeah, just conceptually there's not that much going on in the MLP. It's just like very simple. And again, this is where the model does all of its like actual non-linear computation that is doing creative shit. Now we have the transformer block. This is again pretty straightforward. And end up module. This doesn't even have any weights. So as input, we get the residual stream. I use pre, mid, and post to denote where in the block we are. Then we calculate attention out. Oh yeah, we got to define the layers. So we define so we've got LayerNorm 1, attention, LayerNorm 2, MLP. And now we do self.attention of self.LayerNorm1 of resid pre. This creates, I'll separate them. Though note that not all of these have hooks attached in Easy Transformer. Hook being the thing that lets you get out the activation from inside the model. And now we do basically the same thing, but replacing pre with mid, replacing mid with out, replacing ln1 with ln2, and replacing the attention with MLP. It's worth just like going back and staring at this diagram and just convincing yourself that, yep, resid pre, attention layer, attention out, add to resid mid, MLP out, add to resid post. Note that in Easy Transformer, you get access to all of these. You get access to both resid pre and resid post per block. This should be post. You get access to resid pre and resid post per block, even though resid post of block K is resid pre of block K plus 1. This is just kind of convenient, but like, does make there be a bit of redundancy in wasted storage. I think it's worth the trade. But yeah, let's do our tests. Actually, I'm going to start using a different syntax. Here you can feed in the name of the activation followed by the layer number, and it will also work exactly the same. And if you need to get a specific layer type, you can put in here, but it normally you can just infer unless it's ambiguous. Yep, 100% of the values are correct, I'm happy. Now we do the unembed. Yeah, the unembed is basically just like another linear map creating the output. You could just use NN linear for all of this, but like, I like understanding what's going on internally, and not quite. NN.parameter torch.empty. So we're right multiplying. So left-hand side is always the input, right-hand side is always the output. Then there's a somewhat ambiguous question of whether you should... There's a somewhat ambiguous question about whether you should be including a bias or not. I personally include a bias because GPT-2 does not, but if you're folding in the layer norm for the final layer norm immediately before the unembedding, that creates a bias. So it's useful to just have a bias in here, and all of my models will contain a bias, even though it's initialized to 0. I don't currently have a flag for disabling this. If you're training, it would be very easy to add that as a pull request if you care about it. You would just put requires grad equals 0 here. Or like required grad equals false. Maybe I should just put that into my actual implementation. Now we just do... Let's call this normalized resid final. So what's the shape of normalized resid final? It's residual stream after a layer norm. Layer norm doesn't change shape, so it's the residual stream. Then we just get the logits. Einsum, we begin with normalized resid pre, which is batch position demodel. Then we take demodel devocab. Yeah, that's just correct. I can't bother to type it all up. And then we return the logits. And we're done. So that's all the components of a transformer. We can now put them together. Call this demo transformer. How does the demo transformer work? So the demo transformer needs an embed. It needs a... Yeah, no, that's just basically correct. It also needs a positional embedding. But yeah, so we have a embed, we've got a pos embed. Again, these are just lookup tables. We've got a list of transformer blocks, which we're going to apply in sequence. We've got ln final, which is the layer norm just for the unembed, and we've got the unembed. There are no like parameters in here because it's just using internal things. Yeah, so tokens have shape batch position, I am going to write this out myself, even though Copilot is basically correct. So we embed things, we get the positional embedding, then we take the initial residual string as the embed plus the positional embedding, then we go through the blocks, because they're just a list. Yeah, sorry, module list is just a way you can tell PyTorch, these are all modules inside of you, and I'm going to give you a for loop over them. There's not a neat way to do like self.blocks underscore the index in your range. Note that we want to do a list comprehension here rather than something like transformer block, one element list times n blocks. That should be n layers. Damn it, Copilot. Transformer blocks times n layers, because if you do that, you might end up with the same layer duplicated n times, and that would break everything. Yeah, let's call this residual rather than resid pre, and each block internally is tracking the residual stream thing, and then, yeah, we just kind of return. Yep, this is just a thing. I basically assert that we have just written a transformer. What? What? Did I just forget to add number of layers? So I did. That was anticlimactic. Great. That's a lot of things, because that's a lot of layers. And yep, 100% of the values are correct. If we want, we can just actually use this model. We can just load in the weights of our pre-trained thing. So demo GPT-2 debug equals false. And now we just have a working model. For example, let's give it some text. Let's take the first paragraph of today's featured Wikipedia article, which is about a species of tiny frogs. Great. So here's a random string, the intro paragraph of today's. Yes. I will note that the rest of this video is going to be me showing you can do some cool things to the model, and then showing you how you'd go about training a model yourself. If you were just here to understand transformers, you are done! We have coded a transformer. This notebook will be public along with the video. I recommend go play around with this, and maybe just go and try to code one up yourself. I think writing one from scratch, without looking at the implementation I have in here, except as like an occasional reference, is like a pretty great exercise, and that by the end of that, I think you can credibly claim that you actually understand transformers. So now let's do demo logits for my model. Test tokens. And I need to move this to CUDA, otherwise my model will complain. Oh yeah, I should move this model to CUDA as well. And so now we get the logits. I'm going to do whatever. Now we're going to do write a cross entropy loss function. There is already one in Easy Transformer utils, but I'm just going to write my own because it's useful to just see it done once. So we input the logits and the tokens, and we measure the next token loss. Logits have shape, batch, position, deep vocab. Tokens have shape, batch, position. Hopefully this is burned into your brain by now. We convert the logits to log probs. Cross entropy loss is the average log probability given to the correct token. and it's vaguely principled for a bunch of information theory reasons, because roughly this is the log likelihood of the maximum likelihood estimator, but you completely do not need to understand why this is relevant, you just do it. Now here is the hard part, where you get out the correct log probabilities for the correct token, and Copilot, you've done it again. So what's going on is we can't evaluate the prediction on the final position, because you don't know the beyond final token, so we get rid of that. We can't predict the first token, so we get rid of that. And then we do gather. Gather says, along this axis, take in a tensor which is the same shape as the original tensor along every other axis. Batch position, which contains indexes along the devocab axis, and map this tokens thing to what is the element of the devocab axis at the corresponding position in logits. Gather is really hard to get your head around. I recommend just go read the docs and play around with it. Unsqueeze and squeeze are because these need to have the same number of dimensions, so we add a dummy dimension to tokens and then remove a dummy dimension from tokens. And now we return the predicted log probs. We can just try it. And the model has average log loss of 3.7186. It's pretty hard to interpret these things when you first see them. So the way to interpret this is, if you're trying to predict a uniform distribution with n elements, the best loss you can possibly achieve is natural log of n. So one way you can interpret this kind of loss is there's 50,000 tokens. So you can kind of interpret the negative exponential of the log of the loss as like a average probability, and you can now interpret the uniform loss over the vocab, which is natural log of 50,000, which is something like 8. Now, if we do this, we see that here the average probability given is like 2%, which is like really not that bad. And if we do the loss as uniform over this many variables, this is uniform loss over 41 variables. There's actually 50,000 variables, and uniform loss on that is like 11. This is pretty solid. I feel pretty good about this. We can also use our model to generate things, as we did earlier. We can just take the test logits, take the final thing, argmax that, that's our next token. We can do cute things to this, like, what token is this? New line. That makes sense for the end of a paragraph. We can, for I in range 50, you could take demo logits equals demo GPT-2 of test tokens, and test tokens are, yep. So what we're doing here is we're just saying, let's take our string, let's feed it in, let's get logits, let's feed those logits in, let's take the largest final token, let's convert that to a string, let's add that to the end of our string, and continue. This is going to print an ungodly mess of print statements because of some screw-up I made in the code, but let's just like accept that cell will be a sacrifice. And that was fast. Now we can just print the test string. Wait, what? Oh, okay. The problem presumably, yeah, I didn't append it. So let's regenerate the test string, and then let's regenerate this. I'm going to add a progress bar, because I like progress bars. TQDM is this glorious library that you can just put around an iterator and it will produce a progress bar for you, and I love it so much. Great, what did this do? It has decided to copy the article. Wild. Let's try something else. Test string equals... what's a good thing? Wild. That's a fun thing Copilot has decided to generate for me. Let's try this and see what it does. Why does it keep copying itself? This is terrible. Note that when you're generating, you never want to end with a space because that will fuck up the tokenization. That's a reasonable thing to continue with. What happens if it keeps going? Note that I'm currently generating in a really inefficient way because I'm recomputing on the entire string every time. Because every internal state in the model is only a function of that token and preceding tokens, when you add a new token to the end of the string, all positions apart from the final one are exactly the same, only the final one is new. Lol, what? Cool. I mean, this is a 12-layer model, so it just kind of sucks. So, this isn't incredibly surprising or a sign that our model is bad, but it's a less compelling demo than I'd hoped for. So the final thing I want to show is how you can train a model. Because writing your own training loop for a tiny model is just like actually pretty easy. The key things we got to do here is create data, create model, create optimizer, run training loop. To create the data, you want to download some datasets. The Hugging Face library datasets is great, as is the Hugging Face library transformers, though tragically is not designed for mechanistic interpretability for some weird reason. I made a utility that is the first 10,000 tokens of the pile, so let's do that. So the first 10,000 words in the pile, that first 10,000 entries in the pile as a bunch of text. This is useful because it means you don't have to wait around for a really long time for the dataset to load. We should define a config section, so I can include things like batch size equals, I don't know, 8, and the model config object. Let's say debug equals false, demodel equals, let's make a tiny 2-layer model. Devocab I'm happy to leave as the default. Numheads is 4, dhead is 64 because 64 is the standard thing everyone does. And let's give it 2 layers. And that's a reasonable way to get the devocab. Oh, and let's say our context length is 256. We can do 1024, why not? Now, we're going to create a data loader. So we need to tokenize the text. Tokenizing the text is kind of a headache. In particular, if you want to train a language model, you really want to... the main thing you want to do if you're training a language model is to take in all the text, tokenize it, and then kind of cut things up so they all have length 1024. And then rather than losing things that aren't a multiple of 1024, you like concatenate it to the next text. This has the added bonus that it stops the model learning hard-coding dumb shit like, the second token is often CNN or Reuters, because I've seen a lot of news articles and crap like that. Now, I can do a tokens dataset equals tokenize and concatenate. I don't quite remember what the syntax is, but it looks like it's dataset reference GPT-2 dot tokenizer streaming equals false. Streaming is just like, are you streaming this? Or I can get back to using 256, why not? Streaming is just like, have you downloaded the dataset locally, or are you kind of streaming it in a way that you don't cache it locally? This is a lot faster if you don't need to download a big dataset, but it's slower in the long run, and it means you don't save it in the cache, so you have to have downloading time every single time. And let's add a beginning of sequence token, because that gives our model a resting position, so it's a nice way to train things. So let's print the dataset and print the first element of the dataset. These are good exercises because they just like show you your data looks kind of coherent and not insane. Yeah, so it's downloading the data, download super fast. The two features are text and meta. Yeah, here's a random, I don't know, looks like a news article about a game or something. It's also clearly longer than 1024 tokens. So this tells it what the column name is, and it will return a dataset with a single column called tokens. Yeah, numproc is how many parallel processes to use to do this. Now we just make a dataset. You always want to do shuffle equals true, because if you don't do shuffle equals true, then the same text will be next to itself a bunch, and that means there's correlated data, so the model can like overfit to each data point. So, how many epochs do I want to train for? I want to train for 1 epoch, and I want to print my loss every 10 steps. I need to define the optimizer next, so let's define a bunch of optimizer config. Let's say my learning rate is 1e minus 3. Let's use weight decay 1e minus 2 for kind of arbitrary reasons. You don't really want to use weight decay. GPT-3 used 0.1, so maybe 0.1 is more helpful. I don't know how to reason about this kind of thing. Now we need to define the model. We know how to do this, we did it earlier. And we need to move it to the GPU because it's going to be horrifically slow if we don't. Now we want to create an optimizer. Let's use Atom W. Everyone uses Atom because it's just a good optimizer. Atom W means atom with weight decay. The standard way of doing atom with weight decay, which is the PyTorch default, if you just do weight decay with an atom, is broken for reasons I don't quite understand, but it's unprincipled and bad. Yeah. Now we can just run a training loop. For batch in data loader. You also want the input to the model to be on CUDA. Yep. Oh, I should add a enumerate. The thing here is I just want to print out what the loss is every like 10 steps or something. And if I did it every step, it would kind of bloat this too much. Step C. You want to do dot item because dot item converts a tensor which of a single element to just that element. And dot for F means print out a float with 4 decimal places. Oh yeah, lol, I forgot that it printed loads of shit. New idea. I want to create a list of all of the losses. Yes, I also want to print what the name of the data loader is. Cool, so it's gonna take like I'll take a couple of minutes. So I'll just pause this until it's done. Alright, change of plans. So my VS Code seems to have been crashing because it does not like me trying to print many thousands of lines in quick succession. So I'm just going to call it a day here, but thanks for coming to my overly long transformer implementation tutorial. Hopefully you now have a better understanding of what the fuck is a transformer and how does it work, and how you could write your own. As always, I would be super interested in hearing feedback, and whether anyone actually found this useful, and whether anyone actually bothered watching the whole thing. Thanks!